All right, so welcome everybody. Thank you all for being here. Welcome to the last lesson of Hoon Academy. Lesson 8, building production code and looking towards the future. All right, so to start off our lesson, let's consider this following piece of code, which I will put in the chat for you guys. And I'll bring it up in the editor right here, okay? So let's take this piece of code and save it in our fake ship in the gen folder as primes.who. Okay. Once we save it, we go to our fake ship, we run commit base as we've done before to get that new generator into our fake ship. And now we can run it with less primes, and it takes a number as an input. Let's give it 10. And what's it going to do? It's going to give us all of the prime numbers between 2 and 10. All right, so if we give it 100, we'll get all the prime numbers between 2 and 100. All right. So we're presented with a new piece of Hoon code, and we might want to understand how it works, right? If we're looking at this for the first time, and we have our Hoon Academy skills, certainly we could read this and, line by line, figure out what's going on. However, if you're the author of this piece of code, there's certainly something you could have done to make it easier to interpret, right? And that is writing comments. So if you've come from other programming languages, you gotta be writing comments in your code, right? Helps you and helps others. For any code that's going to make it to the production system, in general, it probably should have some comments in there. All right. The way we write comments in Hoon is we use this col rune. Col is going to make everything after it on the same line as a comment. And if we want to do a new line, we have to do another col at the start of that. So it doesn't multi, but other than that, this is your all-purpose commenting syntax, okay? So let's take a look at a new version of this code where we have augmented the whole thing with very descriptive comments. All right, so now we can take a look at this code and we can perhaps have an easier time understanding it. Okay, so at the top, primes.hoon outputs a list of prime numbers between 2 and the input number. We have a gate right here. It takes an input, which is a pat-ud. And then this line is saying, we're going to create an output. This is going to be the list that we output. And we're going to start off by using gulf to create a list of all the numbers from 2 to the input. Okay, so if you give it 100, you can get all the numbers from 2 to 100. Then we're going to create this counter n, and we're going to use this to filter out every number that's not prime. All right. So we have this bar hep. Remember, bar hep usually means you're doing a recursion. And what are we recursing with? Well, first we're going to ask, is n equal to our input number? So we gave it 100. We're going to ask if is 2 equal to 100 yet? Finally, our comment here says, otherwise, we're going to recurse with the output list filtered out by every number that's divisible by n, unless it's n. So you filter out those numbers, increment n by 1, 2 becomes 3, and then you filter out the multiples of 3, you filter out the multiples of 4 and 5, and so on and so forth. Okay, so that's our very simple algorithm for making a list of prime numbers. It's pretty much the simplest thing you could do. Okay. So we can save this and we can run commit base again. And it's going to work just as before because those comments are not affecting the logic of the code. All right. Okay. So any questions on this piece of code? All right. So when we are building complex pieces of code, there's a lot of different tools that we can and should use to make sure things are working, make sure your intermediate steps are going properly, debugging, and so on and so forth, right? So, for example, in our primes code, if somebody gives it an input of 1, well, there's no prime numbers under 1, right? So the smallest prime number is 2. So maybe we want to say, we want to make sure that the input that somebody gives is going to be at least 2, okay? We can do that with this rune that we will learn. It's called whatgar. Okay? So whatgar is going to take 2 children. If it's like a check or a flag, okay? So it's going to say if child 1, this Hoon expression, is true, then we're going to go on. We're going to do the next thing. We're going to do the rest of our code. If child 1 is false, then we're going to crash our program immediately. Okay? So there's a lot of different uses for these. It's just like, make sure this thing is logically correct at this point in time in the code, right? So in our code here, we might want to say the input is at least 1, right? So we would go here and we would put this piece of code in the on line 7 right here. All right. So this piece of code is saying we're going to get our input and we're going to assert that our input is greater than 1. If so, we're all fine and dandy. We do the rest of this, and otherwise we're going to crash right here. Okay, so we save this. We run commit base to save our changes, and then we give it a 1, we're going to get a crash. And if we give it 2, we're going to get results. Okay. When the code crashes, you may have seen this before. It's going to produce an output trace like this. And it's basically telling you where it's trying to narrow down. If you have several lines of this, narrowing down where that crash occurred. Here, there's just 1 line, and it's saying, look at row 7, column 1. That's where I think your code crashed. And indeed, if we go to row 7, column 1, that's the beginning of our whatgar, which produced the crash. Okay. So that's how you interpret this error output. Okay. So we can also use the whatgal rune, which does the same thing, except it has the opposite logical condition. It says, let me make sure that child 1 is false. If so, then keep doing what I'm doing. If it's true, then we're going to crash the program, right? So we can rewrite this with that rune as well. We want to assert that it's false, that the input is less than 2, right? So if the input is 2 or more, we're fine. But if the input is less than 2, then we have a problem, right? So save this. And then we're going to commit base. And then we'll still have the same behavior as before. All right, just with this different rune, this gal instead of the whatgar. Okay. I believe we might have covered this rune before. The zap rune just immediately crashes the program, right? So if you do zap and press enter in the terminal, you just get a crash. Now you can also write this logical condition with a whatcol and a zap. In general, this, if we're saying if this is false, then we crash. Or sorry, if this is true, then we crash. Otherwise, do this. That's exactly the same as this structure right here. This is saying if this is false, if this is a no, then we crash. Or sorry, if this is a yes. If this is a yes, then we crash. Otherwise, we do this. Okay. So we can also rewrite this section right here as what call less than inputs 2. If so, crash. Otherwise, we're going to do the rest of this program. Okay. So we're saying if the input is less than 2, we crash. Otherwise, we do all this, right? And this is just going to do the same exact thing as before, just a different way of writing it. We crash on an input of 1, and we're fine on an input of 2 or higher. Okay. So any questions on that? That's just 3 different ways to do the same thing, which is have a checkpoint in your code which says make sure these things are correct. Make sure there's some sanity checks here. If so, we'll continue. Otherwise, we'll produce a crash. Okay. Okay. So some other ways to do sanity checks on your programs are with logging to the terminal. You can log outputs to the terminal based on what's happening in your code, and you can see kind of what's going on inside, right? So with the sig bar rune, that's going to say if child 1, if child 2 crashes, if this code crashes, we're going to log this to the terminal. If this works, then we're not going to do anything. Okay, we're going to ignore this. So how can we augment our code here to produce a nice error message? Well, instead of just the zap zap, excuse me. Excuse me. All right, so instead of just the zap zap producing the crash, we can say sig bar, and then we can give its first child to be the text crash because input was less than 2. And then we can have our crashing code right there. Let's save that, commit base, and I'll let you guys read the code. And if we run our primes generator on an input of 1, we're going to get a nice error message, crash because input was less than 2. Okay. And if we give it a 2, then it's going to work as before. Okay. All right. So sig bar, again, that is logging to the terminal when a crash occurs. That's what that's going to let you do. Our next rune, sig pam, is going to always let you print something to the terminal. So it takes 2 children. It's just going to always print this, and it's going to do whatever comes after it, right? So you can always just put sig pams in your code, and it won't affect the logical functioning of the code, but it will produce these side effects of emitting the terminal outputs. Okay. So, for example, something common that you might want to do is you have a recursion, and maybe something's going on in your recursion. Maybe you need to debug it. So you'd like to see the intermediate outputs, the intermediate results at each step of the recursion before you get to the end, right? That might help you understand what's going on. So we can do that in here. We can say, inside of our recursion, let's always print the intermediate states of the output list to the terminal. Remember, the output list we started with a list of all the numbers from 2 to our input. So if we gave it 100, it'd be a list from 2 to 100, right? And in every step of this recursion, we're going to say, okay, let's filter out all the multiples of 2. Then let's filter out all the multiples of 3. Let's filter out all the multiples of 4. Let's filter out all the multiples of 5, so on and so forth, right? So if this is working correctly, we should see that list of numbers, but with different multiples being filtered out of it at every step, right? So let's save our input, and let's commit base to push those changes. And then let's run primes on an input of 10. And indeed, so we are seeing at first we're starting off with all the numbers from 2 to 10. Then we filtered out all of the multiples of 2 that are not 2. So we filtered out 4 and 6 and 8. And then we filter out all the multiples of 3, which are not 3. So we just filtered out 9. And then there's no more filtering. At each of these recursive steps, nothing else is being listed. Okay. But that shows you how this algorithm produced our final results of 2, 3, 5, 7 when we gave it an input of 10. Okay. So any questions on that? So again, SIGPAM is what you use when you always want to print something to the terminal inside your code. Okay. Okay, so one final neat trick about logging is you can actually change the colors. Okay. So if I want my terminal logging to be green, I put this single gar, this right caret in there, and then I'll get green. If I put two of these, then I commit base, and I'll get yellow. And if I put 3 of these, I will get red output. Okay, so neat little trick if you want to have colors show up in your terminal logging. Okay. So just put this right here before the thing that we're printing the terminal, and that changes the color. Does that work for SIGBAR? That's a great question. So it should work because it used to not work, but there was a patch that should have made it work. So let's see. I believe this is patched, but it might not be up to date on my current version. So, okay, it seems like it's not working, but at some point I believe it was changed so that it does work. It should work for a SIGBAR. I can get back to you on that. But good question. Okay. So unless there are any other questions, we shall be moving on. So in Hoon, much like in other languages, you can save pieces of code and import them as library files, which you can use throughout other pieces of code as utilities, right? If you've programmed in other languages, you may be familiar with this pattern. And that's just to save you the space of repeatedly writing some script that you might use, right? So let's use a library file with our generator here. Okay, so let's maybe say this thing, which is filtering out numbers. This piece of logic, maybe let's abstract that out to a library file and let's import it and use it. Okay. So let's make a library file. It's going to be our library file is going to be a core with a single arm. Of course, you can have as many arms as you like, but it's going to be a core. In this case, just a single arm. And that arm is called filter. It's going to contain that filtering logic that we use in our primes generator. Okay, so let's save this as primes-lib. Okay. Now, how do we use this in our primes generator? So what we're going to do is we're going to use this room called baslus right here. is the room to import something from the lib folder. And the thing we need to import is primes lib. Now, the way that we call something from primes lib is going to be this syntax. So you may be familiar with this syntax right here. This is sugar for the tis gal, right? So this is saying in the context of this core, we want to pull this arm and use that, build that arm and use it, right? So that's what we're doing here. If you put a tar in front of this import, well, let's show you that this works. Okay? So I'm going to run commit base, and then I'm going to run my primes as before, and that's going to work with this library import. Okay, so now if you want to directly access the namespace of this library, so you want to be able to name all those arms without always having to refer to the library, you put this tar in front right here, that tar, and then that will let you just directly call filter. So let's commit this, and boom, it works just as before, with directly calling that arm of that library. Okay. Any questions on that? Okay. So something else we can do, we can also import our library files into the dojo to use them. Unlike generators, library files aren't immediately available in the dojo when you commit your changes, but you can import them also with this fazlas room. So I want to import primes lib. I can do that with fazlas as well. Same room here. You then have to call it a little differently. So you have to do filter cold primes lib. So that's the same as before. We're calling the filter arm of the primes lib core. You also have to do cold lib. That's telling you that this is something that we got from the lib folder. But then we can use this just as we use it in our generator. And indeed, we are calling this arm of this library that we imported. We have this list 1, 2, 3, 4, 5, 6, 7, 8, and we filtered out 4, 6, and 8. Okay. Okay, so we made a library file, and we showed you how to import it into our generator and use it, and we also showed you how we import that into our dojo, and we can call it from the dojo as well. All right, so are there any questions on that? Okay, so moving on, there's one concept that we should briefly cover before we get into our next section, which is testing. Okay, so we're going to introduce a new data structure, which is called a base. Okay, so a base is pretty simple. It's just a cell of two things. The head is a type, and then the tail is a thing. So it's just a pair, the type of thing and the thing. All right. So you can put something in a base with this room zapgar. Okay. So for example, if I do zapgar, the number 2, we're going to get a pair that's saying this is a PAT-UD, and then the tail is number 2. Okay. So if we use zapgar planet Zod, we get a pair that's PAT-P and telling you that the number underlying Zod is 0. All right. So that's a base. We put these two values into bases, and that's how they look. Okay. If you have a base, you can also extract its value and cast it to the type with this zapgal room. So for example, if we put Zod in a vase here, and then we extract it to a pap p. Oops, sorry. There we go. So you put Zod into a vase, and then we extract it into a pap p, then we get back Zod. So we are going to use the concept of vases in our next section, which is about unit tests. Okay. So testing code is a very important part of shipping clean, high quality software, right? So let's write some tests and use some tests for our primes generator. Okay, so first thing we're going to do is we are going to let's go to our base desk, and then let's make a new folder called test. Okay, and that's where we're going to have our test files. Okay, now let's go to our code editor, and let's take this piece of code and let's save it as primes.hoon in that folder. Okay, let's take this piece of code, go to base and the test folder, and we're going to save it as primes.hoon in this folder. All right. Okay, so big piece of code. Let's break this down and let's understand what's going on in here. All right. So first off, at the top, FASLUS tar test. As we just learned, FASLUS is the room to import a library file, and that tar, so we're importing a library called test, and that tar in front is going to say we want to access that namespace directly. We want to be able to name the arms inside of that code. Okay. Next line, FASTIS. We haven't seen this room before. What this does is it lets you import any Urbit file. Okay, so we're building and importing any .hoon file that we can find. In this case, we are saying, let's go to the primes file in the gen folder, so our primes generator, and let's import it under the name primes. So we're building that file, and we're building it under the name primes so that we can access it inside of this test file. Okay, that's the thing we are testing. Next, this is the rest of this code is one big core, and it has 4 arms, and each of the arms of the core has the word test in its name, and that will let the test thread on the test runner know that these are tests that we want to run. Okay, so there's 4 arms here, and those are 4 tests. Okay. So let's take a look at this first test, test 01. So first, we're doing a sendLus. Remember that sendLus is the room to call a gate that takes 2 arguments. Okay, so we're going to call a gate expect eq, and expect eq is from the test library that we imported up top. Okay, so this is from here, and we can reference it directly because we put this tar here. And what does this do? Well, it takes as input 2 different vases, and it's going to make sure that they're equal. Okay, so remember, vase is a thing that we just learned about, pair of type and the noun. Okay, so what are we making sure is equal? Well, the first argument is going to be the expected value. So in this case, our expected value is a list of PAT-UDs 2, 3, 5, 7. And we're putting the zapgar at the front to put it in a base. And then the second argument is going to be, what do we expect to be equal to that? Well, we want the result of calling primes on an input of 10 to give you the prime numbers 2, 3, 5, and 7. Okay, so we're also going to put that in a base with this zapgar up front. And those are the two arguments. So you're calling this gate from the test library on these two arguments. Okay. The rest of these, test 1, test 2, and test 3, those all have the same structure. So test 2 is saying on an input of 2, I should have a list just containing 2. And on an input of 50, I should have the list containing all these prime numbers up to 50. Okay. So test 1, test 2, test 3, similar structure going on. Okay. They're all using this expect equal. Now our final one, test 4, is a little different. Okay. And in this case, we want to test that our code should produce a failure on a certain input. Okay. Recall that we changed our code so that if you give it an input of 0 or 1, it should be crashing, right? That's what we want to happen. So how do we test that our code is should be failing? Well, we call the expect fail gate from the test library, and that just takes one argument. And that argument is the code that should fail. Okay. Now, instead of just directly giving that failing code, we want to wrap it inside of the core. And bardot creates a single armed core and puts that its arguments into the single arm of the core. Now, remember when we learned about cores, it was an important fact that the code in the arms of a core aren't run until they're called. They're like lazily evaluated, right? So that means that when we put this crashing code into the arm of a core, that's going to help us because it's going to say, don't run this yet. We only want to run it in a controlled environment. We don't want it to actually crash the test thread. We want to put it in a sandbox and then run it and then make sure that crash is occurring. Okay. So those are the 4 arms of this test file. So let's actually run this code. Okay. So you run bar commit send base, and we want to run the test thread, which is our test runner, which is going to run this file. Okay. Threads are transient computations that live in the TED folder, TED. So go to Urbit, base, TED, TED. These are all different threads, okay? And you can probably see that the test thread is right there. Okay, so we want to run this thing, and we want to run it with an argument of our primes.hoon test file that we wrote. Okay, so syntax is going to look like this. This hep test say run the test thread, and the argument we're giving it is the location of our our test file. So this is just in the directory that it's in, and this is the name of the file, right? This sen up front, this character is a shorthand that references your current ship, your current desk, and the current time. Okay, because you can specify, you could actually specify, oh, run this test thread that's on a different ship, or run it which lives on a different desk than the one I'm currently on, or like an older version of it. But since we usually don't bother with that, we're just, everything's the default arguments. This is just a nice shorthand, so you don't have to write that all out. Okay, that's what this is. There's another way of writing that, which looks like this. Just these three equal signs, three tis. They're saying default ship, default desk, default case, or the current time. Okay. So if we run this, it's going to take a second, and then we're going to get all of these OKs. We're going to get test 1 passed, test 2 passed, test 3 passed, and test 4 passed. Okay, so all these prints are from our print statements here. If we want to remove those, that will make this a little bit neater. And there you can see all 4 tests are indeed passing. So our file is working as intended. Okay. Are there any questions on testing? Here's the code, and here's the outputs of running our tests. All right. There's no questions. We shall be moving on to our next topic. Okay. So far, we've learned how to work with generators, right? And the generators we've been working with are what's called naked generators, regular generators. We've written them, we've saved them, and we've run them from the dojo, right? Actually, most generators that we'll encounter in the system are something slightly more sophisticated, called sensei generators. Okay, so sen sign and then say generators. So let's understand what those are. First, let's start by looking at a simple example of a regular naked generator. Okay, so what does this generator do? Well, it accepts anything as an input, and then it simply returns the number 42. Okay, so let's write this, and then let's save it as in the gen folder as example. So we save it, run commit base, and then we can run example with any input, and it will return the number 42. If we try to run it without giving it an input, it's going to say, actually, I need an input, and it's going to throw an error. So you need to give it something, but it's always just going to return 42. Okay. Very simple, kind of brainless example of a generator, right? How would you write this as a sensei generator? Okay. Well, it'll probably look something like this. So what's going on here? First, we have this Cohort that's room to make a cell, and then we're making a cell whose head is a tag sensei, and its tail is the rest of a generator. Okay, so we're making a cell. The head is a tag sensei, tail is a generator. Next, we have a generator. It takes anything as input, but inside of it, we're not just directly returning the number 42. We're returning a pair of send now and 42. So what's going on? If we take this code and we save it in our example generator, and then we run commit base, and then we can actually now run our example generator without giving it any argument at all. We can just do less example, and we get the number 42. We can also give it an input, and we can get the number 42. So that's pretty neat, right? That's kind of different from the generator before, right? So what's going on here with these sensei and the send now? So it turns out these are metadata tags for the Urbit system. And putting your generator in the cell with a tag is just going to pass some information to the dojo saying this is a particular kind of generator. You don't actually output that information, but it is going to read that and know what to do with it. Okay, so in this case, the sensei is saying, this is a say generator. That's what it's telling the dojo. This is a say generator. You can treat it a certain way. And inside here, we're not just directly returning the result 42, we're returning it with what's called a mark. So a mark is like the Urbit equivalent of a file type. And in this case, we're giving this number 42 the most generic file type possible, which is that it is a noun. Okay, so again, this is saying we're wrapping our generator with the tag sensei, and then we're wrapping the output with this tag saying it's of type noun. Okay. And again, they are parsed out, so that's why you just get the number 42. You don't actually see any of these tags when you're using it. So in this example of a generator, the sample here, the how you could think of input to the gate is just tar, and that stands for any noun, right? So that's the most generic possible example of a input, right? Sensei generators actually have a very sophisticated type of input that you can give it that consists of 3 different parts. Okay, so in general, the sample or the input to a sensei generator is going to have these 3 parts. The first is itself a triple, which contains 3 useful pieces of information. That triple is going to have the current time, environmental entropy, which is randomness that you can use to generate a randomness within your generator, and also the beak, which tells you some information about the current location, like your current path within the ship. Okay, so this is just what we saw before when we did like this syntax. That's that triple, which is saying our current planet, our current desk, and the case, which is the current time, generally. Okay. So kind of a fun fact is that like this triple is, you'll see this often in Urbit development, and this is called what's called the bull. And they're lumped together because Urbit is a deterministic system in that you have basically what are functions that will always produce a certain output when you give it a certain input. However, like actual computers, they have to deal with non-deterministic stuff. Like for example, if you want to generate randomness, that's non-deterministic. The current time of day is not, if you run a generator this year and you run it next year, it's not going to know what time you're going to run it. So that time of day always changes, right? So this is a way of lumping together all the non-deterministic information that your generator might need into one argument. Okay. So current time, generator sample. You can specify arguments that are required. Okay, so that's going to say to run this, you have to have these arguments. You can also have nothing here, so that will let you run your generator without any arguments. And finally, something that you can't do with a regular generator is you can specify optional arguments. Okay, so these are arguments that if you provide them, the generator will use them, and if you don't provide them, then they'll be a default value or something like that. Okay, so with these 3 together, that gives your say generator a lot more flexibility than your regular generator would, and that's why they're kind of a special thing that is often used when writing generators. Okay. when you're writing a state generator, you can use any parts of these that you need and discard the rest. So, for example, if you just write a tar, well, that's the most generic type of a noun. This will fit a tar. So this, you can just say that the sample is a tar, right? Just like we did here. You can say, maybe I just need the current time. I don't need this, I don't need this, I don't need these. Well, that's what's going on here. You can also say, I don't need this information. I just need two required arguments, text and planet. All right. And you can also say, I don't need this or this, but I do need one optional argument. That's what this would look like as a sample. Okay. So basically just saying that you can customize this to whatever your script actually needs. Okay. Okay, so let's dive a little deeper into one of these arguments that we mentioned, and that's the environmental entropy. So this lets us use randomness in our state generators. And what this any is, it's actually a random seed. So let's go through an example where we actually use this random seed to generate random outputs. Okay. So let's take a look at this piece of code. And let's save it in our gen folder as dice.hoon. So we save this in our gen folder, we run commit base, and then let's try it out. So our dice generator, it needs one required argument, which is n, and then one optional argument, which is a bet. Okay. So we're going to do less dice, and then we'll just use the argument. Let's say six-sided dice, and we are generating random numbers between 0 and 5. Okay. And the reason it's saying you won $0 is because what this does is it rolls that number and then multiplies it by the bet number that you gave it. Since we didn't give it a bet number, it's going to use the bunt or the default value of that variable, and that's going to be the number 0. So 0 times anything is 0, right? If we want to actually bet some money here, we can use this syntax, just saying, are using this optional arguments. Let's give it a value of 100, and let's roll our six-sided dice to win $500, $400, $200, 100, 0. Okay. So that's what's going on in this piece of code. Now, let's break down how this code works. Okay. So to start off, we have a Cohort and the sensei, which is a head tag to make this a sensei generator. Okay. Next is the rest of the generator code. Inside of the generator, we're going to tag its output with the mark send now, which is just the most general example of a mark or a file type. Okay. So here's the sample of our generator, which is a little bit more sophisticated than what we saw before. Okay. So here we're saying we're going to use this now, any, and beak. Okay. So we're going to use the current time. We don't actually use it, but it's named there. The current time, the environmental entropy, which we do use, and the current path. Okay. Next, we have our one required argument, which is specified, just the number n, which is a pat UD. And we have our optional argument, bet, which is also a pat UD. Okay. Next, inside of here, this is going to generate a random number between 0 and this value n. And it's going to store it under this phase role. Okay. Next, it's going to print a message to the terminal. You won mole roll bet. So you got a random number, you multiply it by the bet, and then you're going to put that into this text string to output that to the terminal. And then finally, you're going to output just the actual random number that you generated. Okay. So let's, I glossed over a little bit what actually is going on in here. We should actually understand how this, what is this rad OG, and how do we actually generate this random number between 0 and 10. Okay. So you may be familiar with the syntax. It may look familiar. We have a door called OG, which is our door for dealing with different types of random numbers. Okay. And we're going to call its arm rad, RAD, with the sample NA, which is our environmental entry. Okay. This syntax creates a gate, and that gate takes any PAT-UD number and then gives you a PAT-UD between 0 and that number. So in our case, we called this gate with an input of 6, and we got a number between 0 and 5. Okay. This any is actually just a big random number that Urbit gets from the Unix process that it's running on. So it's pinging Unix and asking for that randomness to be handed to it. And in Unix, they actually create this randomness with something that's called CPU jitter. So basically, like, the random fluctuations of your computer hardware is actually where this random number is coming from. So if we get that any and we cast it to a pat, we can just see that it is indeed a big number that is changing pseudo-random. Okay. Now, so that big number is passed to this OG door, and then we're calling the rad arm, and then that's how we're going to get a number that is pseudo-random here. So you want a number between 0 and 10, then that is the syntax. Okay. Since any is just a big number, we could have actually just put some number here. Like, you can just put the number 1 as your random seed, and that will make this output something between 0 and 10. But the problem there is, if you don't change that random seed, the output doesn't actually change. So this highlights the point that the randomness is coming from that random seed varying and not from the logic of rad or OG. That is a part of the Urbit deterministic system. So whenever you give that the same input, it's always going to give you the same output. So to get pseudo randomness, you have to get different inputs. Okay. Do we have any questions on that? Okay, so if there are no questions, let's move on to the final section of this course. So Liam says, can an Urbit be run on bare metal? If so, how is the randomness generated? So today, Urbit only runs on top of Unix, but there are efforts. Motfel Winrux at Native Planet, he is working on a way to run Urbit on bare metal. It's not fully realized yet, but if that were the case, then yes, you would have to implement the the random entropy somewhere where you get it directly from the system instead of routing through Unix to get that. Yep, good question. Okay, so unless there are any more questions, we shall be moving on. So in this final section, let's take a moment to look ahead to what comes next after Hoon Academy. Once you've completed Hoon Academy, you're ready to learn how to build both standalone programs and even contributions to the core Urbit system. So Urbit is what's called a state machine, meaning its entire functioning can be understood as a system which has some state, receives some input, and that makes it transition to a new state that possibly also emits some effects, okay? So it's at a state, it's like a solid piece of something. You give it some input that makes it move to a new state, and that maybe creates some side effects, maybe shows something on the screen, logs something in terminal, so on and so forth, right? In particular, since every substantial piece of code in Urbit is a core, in practice, this looks like a pair of input and a core changing to a pair of effects and a new core, okay? So this is the pattern for which every substantial system on Urbit is implemented. So let's see a basic piece of code that models this pattern, okay? Let's take a look at this piece of code, which is called, we're going to call it Tiny Agent, okay? So, so let's take a look at this and understand what's going on in it, okay? So this whole piece of code is a door, or as we learned, that's a core which has a sample, okay? In this case, this door has a sample, which is a single number, single pat UD called balance, okay? It has an arm, which is named this. And then the definition of that arm is just a dot. So what's going on there? Recall that when an arm of a core is evaluated, it's evaluated with respect to its parent core as a subject, okay? And remember that the dot syntax refers to the entire subject of a Hoon computation. So what this does is it says we're going to alias the entire subject, which is in this case the entire door, with the name this. That means that in the other arms, I can call something this this, and that refers to this entire door. Okay. So this is a little piece of infrastructure. That's what this lets you do. Okay. So next, we have three more arms: on init, on poke, and on peek, and those define the fundamental operations of this tiny agent. Okay. So on init is how you might initialize your app. It contains a gate, and that gate takes a single number and then returns this entire door with balance set to amount. And recall that this syntax right here is the sugar syntax of sentis. So that in tall form would actually look like sentis, this balance change to amount, and then tis. Okay. So this syntax right here is this expression in sugar form. Okay. So what are we doing? We're creating a new copy of the door. This gate is going to return a new copy of this door with that balance set to whatever amount you want to pass in. Okay. Does that make sense to everybody? So again, this gate takes a number, gives you back this whole data structure with that balance set to something. Okay. Now, the next arm, on poke, this is how you handle inputs to this state machine. Okay. And this is where the main logic of the app is occurring. Okay. So on poke, it contains a gate, and that gate takes as input a pair. The head of the pair is a tag that's either send add or send sub. And the tail is an amount. So that means the input here should be either send add and some amount or send sub and some amount. Okay. That's what you should be calling the onPoke arm with. Next, inside the logic, we have a switch statement. We're saying we're going to change our behavior depending on what that tag was. Okay. We're saying if the tag was send add, we are going to create a new copy of the store, except with balance changed to the balance plus the amount that you passed in, right? So again, this syntax is a sugar syntax for this send tis, and that's creating a new copy of this whole data structure with that balance change to something else, okay? And if the tag was send sub, very similar logic. We're creating a new copy of this data structure with balance changed to minus whatever amount you passed in, okay? And that's the entire logic of the onPoke arm. And finally, the onPeak arm just lets you read the state without making any changes to this data structure. And there we're just going to return the value that's in balance, okay? So let's see how we actually use this tiny agent. So the way that we use this is we're going to take this piece of code, we're going to take this door, and we're going to set it as a subject with this and we're going to call the onPeak arm. Okay. And that's going to give us the value 100 because we took the original door, we changed the value to 100, and then we looked at the value. Okay. We can do a more complex series of actions. So here, we're setting this door as a subject. Then we're going to create a new copy of it with initial value 100. We're going to set that as a subject. We're going to create a new copy of it where we subtracted 3 from the bank account. Then we're going to set that as a subject, and then we're going to create a new copy of it where we add 20 to the bank account. And then we're going to finally call the onPeak arm to look at our final balance, and that's going to be 117. Okay. And instead of chaining all these tisgars where we repeatedly set something as a subject, create a new version of it, set that as a subject, create a new version of it, so on and so forth, there's actually a rune that we can use to simplify this, and that's the tis-sig rune. So whenever you have this repeated composition with this tisgar, you can instead use this tis-sig and do that in a cleaner way with just one rune. So to rewrite this, this is just doing the same exact repeated composition, except you don't have to put a tisgar in front of everything. Okay, so all we're going to do is we're going to do tis-sig, first our original door, the door with initial value 100, then the door with 30 subtracted, then the door with 20 added, and then we're going to call onPeak. And that's going to give us the same thing, which is 117. Okay. So in conclusion, this is a simplified bare bones version of a pattern, which you're going to see throughout all the apps in Urbit and even the core Urbit state machine itself. Okay. So that brings us to the conclusion of this lesson and all of Hoon Academy. As far as entire operating systems and network protocols go, Urbit is pretty small and simple. And as a Hoon Academy finisher, you're getting a great basis to start to understand the whole thing. Urbit is a growing and evolving system. We're still under construction. Don't consider anything you've learned in this course to be frozen, because this is early stage open source software. And if there's something that you don't like, if there's something that could be better, if there's something that you want to exist, we want you to jump in and change it. Okay. It's important for you guys to cultivate a sense of agency because you will be essential for the future of this project. You've hopped on the ride to making a new foundation for the internet, and you can help steer it too. As you may know, we have a grants and bounty system where you can do work and earn stars, which are parts of the Urbit network. Each star has about 65,000 planets there, and there's about 65,000 stars total, and you can earn several stars for making a unique contribution to the Urbit ecosystem. Okay. Doing the grants program is a great way to get noticed and work your way on up through the ecosystem. And that's how I started out. That's how I got on the path to working this job where I get to teach you guys. All right. If you ever want to discuss what to do next on the network, always feel free to reach out. I'm always happy to discuss that. Okay. So I really look forward to having you guys around the network and even at Urbit events. And I'm very excited for what you're going to build with your new Hoon skills. All right. So thank you guys very much. And that is the end of the course.
Thanks, Jen.